Hello and welcome wherever you are to the 30th Orkney International Science Festival. My name's Howie Firth and I'm representing a festival team that's spread through Orkney and across the north as well, with many good people helping us in this new adventure of online delivery. It's morning in Orkney and across Scotland, but some of our visitors may well be in a different time zone. And indeed, it would be interesting to hear where you are through YouTube's live chat. We've a varied programme with the sound of the sea running through it with the year of coasts and waters. We have a rich mix of events for Foraging Fortnight as well. We feature each year a lecture to the memory of a great Orcadian who died 50 years ago. John D. Mackay, the headmaster of the school in Sandy. He was a man of great learning and vision who loved to explore new insights from the past and to look ahead at possible futures. And our speaker this morning connects both past and future. Professor Tom Stevenson spoke in the first Orkney Science Festival back in 1991, and he has the unique distinction of having spoken in every one of the festivals that have followed. And he's joining us today from his home in Roslin, outside Edinburgh. Good morning, Tom.
Good morning, Howie. Good morning, everyone.
Tom, you were born in Quailoo, you went to Stromness Academy, and then it was Aberdeen University, the next step after that?
That's right, yes. I left after fifth year and went to Aberdeen University.
And you studied, was it physics?
It was physics, yes. It was called natural philosophy in those days. I had the privilege of being taught by Professor R.V. Jones, who had been a scientific advisor to Churchill in World War II. He was a brilliant teacher, brilliant speaker.
That was Professor Jones who was involved in weapon development.
Well, scientific intelligence, really, trying to figure out what the Germans were up to, what their next weapon was going to be like, and so on.
And then after that, there was a period for you in the electronics industry.
Yes, I went from there to Ferranti Limited, their place at Dalkeith, just outside Edinburgh. I was there for 6 years. And then joined Wolfson Microelectronics, which was a spin-out from the University of Edinburgh.
And then while you were there, you completed a PhD.
Yes, I joined the electrical engineering department in 1980. And while I was still working there, I was able to do a part-time PhD whilst working in microelectronics research.
And in your early years there, you completed a PhD.
That's right, yes. I was able to do that whilst employed by the university.
And by the time you retired in 2012, you had a general chair in microelectronics technology.
That's right, a personal chair in microelectronics technology. And by that time, we'd moved into a new building and we were rebadged as the Scottish Microelectronics Centre with a suite of clean rooms and associated facilities.
And you were operations director of the centre?
Yes.
Also, Tom, I should add your long involvement with the Museum of Communication in Burnt Island in Fife.
That's right. That came about because a former colleague, Harry Matthews, at electrical engineering at the University of Edinburgh, was an avid collector of initially old wireless sets, and this grew and grew into a huge collection. And he later transferred ownership of that after he retired to a trust, and I was one of the original trustees. And that was 25 years ago, and I'm still there. So it's been a long association, yes.
Well, Tom, you're the ideal person to open the festival and to give this lecture in which you're going to look back at some of the developments in technology over the past 30 years and forward to see what the next 3 decades might have in store for Orkney. You'll be looking ahead in the title of your talk, As Far as Thought Can Reach.
Well, good morning, ladies and gentlemen. I regard it as a great honour to be asked to open this 30th Science Festival and also to do the John D. Mackay Memorial Lecture. Howie and his team are to be congratulated on putting on this event online due to the coronavirus pandemic, and we hope that it will be successful and attract a large audience. Now, Howie asked me to look back and look forward. Looking back to the first Science Festival in 1991 and looking forward to what things might be like in 2050. Now, in 1991, a colleague, David Renshaw, and I spoke about this device, which was a single chip video camera, which would be the forerunner of the cameras that are now in all our mobile phones. So I'll be talking a bit more about that in the next few slides. But going back to 1991 again, that Science Festival was opened by Professor Heinz Wolff, and this is how he might have looked in 1991. At that time, he was a very high-profile television personality, rather like Brian Cox is today. I worked with Heinz on several lectures in subsequent years. He was really a brilliant guy and great fun to work with. And this is a picture that I took on the occasion of his 80th birthday in April 2008 at Brunel University. Sadly, he died just before Christmas in 2017, and he will be greatly missed by the science community. Looking back to 1991, most personal communications were by letter or telephone. There was no internet at that stage, no email. Companies, commercial organizations were using fax machines, facsimile machines, and of course computers had come in around about 1980. The IBM PC came on the market and many companies were using these. Now the first lecture that we gave at the Science Festival in 1991 was in the Air Hotel, and I was joined by David Renshaw. We did a double act entitled Electronics in Miniature, which just means microelectronics. The microelectronics industry at that stage was about 20 years old. And we described how millions of transistors could be made simultaneously on wafers of silicon. I covered the manufacturing process whereby millions of these things, field effect transistors, could be printed and etched and processed on the surface of silicon wafer and then interconnected with a metal pattern, perhaps like this, to create a very complex circuit. And this is a photograph through a microscope of the corner of an integrated circuit. And you can see here arrays of transistors, and they're interconnected by these white tracks, which are in fact aluminium metal. Now the device that David described had been designed by David and a colleague, Peter Denyer, and it had this made. This is a silicon chip here, which is an image sensor that produced a monochrome image, television image. It required just a single 9-volt supply, and it had things like automatic gain control, automatic exposure. And they had formed a spin-out company, seeing the potential of this, called VLSI Vision Limited, or VVL for short. Now, I'm going to tell you the story of the background to this camera because it's really typical of the sort of things that can happen in high-tech research. Peter Denyer had an idea for a fingerprint lock. We all carry lots of keys around, and he thought, wouldn't it be nice if instead of having a keyhole, we had a pad on the door, which you just put a finger on, and that image of the fingerprint would be compared by a computer with a stored image, and if you were allowed in, it would open the door. His inspiration for how to capture the fingerprint came when looking into a glass of beer. If you look down into a glass of beer, if you get the lighting right, you get a very clear image of the texture of the skin on your finger. And the first task was find a way of capturing that electronically. So you can't obviously have a glass of beer on every door. So what was lashed up was a prototype with a prism. The reflecting face of the prism is the equivalent of the glass surface on which Peter had seen the fingerprint. We have an extended light source, and the camera at the right-hand side here was an existing commercial video camera, which was about half the size of a shoebox and cost several £100s. Now, this was a monochrome camera, and it was pretty obvious that for wider applications other than fingerprints, a color camera was required. And for this, the science was all sorted out by James Clerk Maxwell, who demonstrated color photography in 1861, would you believe? He was an absolutely brilliant scientist. And he showed that you could produce a full color image if you took 3 simultaneous images, one in red, one in green, and one in blue light. So to get a full color camera, adjacent pixels or picture elements, these are the sensor picture elements on the monochrome chip, adjacent pixels had to be coated with color filters, colored resins. And that was indeed done. Now, at this point, I should mention that the fingerprint lock idea did not take off. It was not commercially viable. But Peter had the idea of putting a color camera in a mobile phone. Now, nowadays, phones have more than one camera, usually at least 2 and sometimes more nowadays. The main camera takes the good quality image, and there are usually separate cameras for FaceTime and things like that. Now, these are very small. Here we have 2 of these cameras, chips, on the surface of a 5-penny piece to give you an idea of the size of it. And for a bit of fun, I took a picture of myself taking the picture here. So that's where the selfie camera is on the front of the phone. Now, VVL was a great success story. It was floated on the stock market. The color cameras were developed around about 1993. By 1997, they had supplied over 1 million cameras for phones. They'd also supplied chips to go into an optical mouse. And the company was bought by a French company, ST Microelectronics, for £23 million. The design team is still based in Edinburgh. They're still developing new cameras, but they are no longer in the phone market, which has become far more competitive. They moved into much higher tech cameras. Now, in the intervening 30 years, microelectronics has moved on a long, long way. And the drive has always been to try to make things smaller, try to get more complexity into the same space. And we need to now talk about dimensions. We all know about meters. A meter is about 3'3". If we divide that into 1,000, we get millimeters. And these are the graduations on the side of a ruler that old folk find difficult to see without their glasses. If we divide the millimeter by 1,000 again, we get micrometers, or microns for short. And then if we split the micron by 1,000, we get nanometers, or NM for short. Now, these numbers may not mean anything to you, but to give you a feel for it, a human hair is between 50 and 100 microns in diameter. And the wavelength of visible light is about half a micron, or 500 nanometers. So why do we want to shrink things? Well, if you look at an area of integrated circuit like this, supposing you can make every feature smaller by a factor of 2, a linear factor of 2, then you can see that the same area of circuitry could be put into 1/4 of the area of silicon. And this means that the cost per transistor will come down by a factor of 4 as well, very roughly, because the cost of the circuit is really proportional to the amount of silicon that you use, the area of silicon that you consume. So there's a cost factor driving this to make things smaller, therefore cheaper. Now in 1991, an advanced circuit would have had the smallest feature around about 1 micrometer or 1 micron. And today, an advanced circuit would have features as small as 10 nanometers. Now that's a linear shrink of a factor of 100. Or if you applied a very simple cost model, a cost shrinkage of a factor of 10,000. This is why we're able to buy enormously complex devices at relatively low cost. But this shrinkage and cost reduction doesn't apply to cameras, because on cameras, the sensor size, that is the pixel size, has to be about a micron or so, because the wavelength of visible light is half a micron. And if you tried to make pixels that small, they simply would not work for all sorts of good optical reasons. Now, another area where this shrinkage and cost reduction has been dramatic is in data storage, solid state memory storage. If you have an Encyclopedia Britannica on the shelf, that is roughly 1 gigabyte in digital terms. But nowadays we can buy memory sticks and SD cards with multiple gigabyte storage for just a few pounds. Now, to put this in physical context, here's a logarithmic scale of dimensions along the bottom here, with a human hair along at the left-hand side here in the sort of 50 to 100 micron diameter, bacteria around about 1 micron, viruses, which are in the news, round about 1/10 of a micron, 100 nanometers, and right down to atomic particles, which are fractions of a nanometer. And here in the middle, I've put in a transistor, field effect transistor, with a gate length of 35 nanometers. And that's the sort of thing that is in these memory storage devices, and has given us this enormous packing density of information. Now, this continuous shrinkage was noticed by Gordon Moore of Intel many years ago, way back in the 70s. And he noticed that the number of transistors on a chip was doubling roughly every 2 years. And this has led to what's called Moore's Law. And it's still happening. You can see here from about 1970 up to the present time, we have had an enormous increase in the complexity of circuits. This is a logarithmic scale, by the way. This is going in factors of 10. And we're right up here at something like 100 million transistors per square millimeter. It's an enormous range of complexity in just 50 years. So, to summarize, in the last 30 years, things have changed dramatically due to microelectronics and this high technology. There are a lot more personal computers. We now have internet, email, and broadband, and social media, a new thing entirely that has appeared within the last few years and is now very much to the fore in most people's lives, apart from me, that is. I've mentioned digital cameras and mobile phones. We also have satellite navigation, GPS, on our phones. And in Orkney, we've got a lot more renewable energy generation. And taking a global view, there are a lot more people in the world. So looking to the future, Howie's asked what inventions might be taking shape that are going to change our lives in 30 years' time. Very hard to say, because there may be some completely novel and disruptive thing that takes things in a completely unexpected direction. But I'm going to play safe today and make some guesses based on known trends. An example of a disruptive change here, my slides for 1991 lectures were done on 35mm film. And global sales of film peaked in 2001. Then along came digital cameras, and the change was so rapid that it even caught out Kodak. Kodak did not anticipate the drop in demand for film, and they went bankrupt in 2012. But now, the cameras in mobile phones are so good that sales of the cheaper digital cameras have gone into decline, because people are using their phones to take entirely adequate photographs, and they're quite happy with that. So what can we say about world conditions in 2050? Well, we can say that there will be a lot more people. We'll probably have better communications. The average age of the population will be higher. We'll have a lot less oil and gas left, and we're going to pay more for food, travel, water, and energy. Now, Orkney is very well placed for food and water and energy. We've got plenty of it. But we'll be subject to global pressures on price and so on. And this picture here at Stove Quailoo really summarizes some of the issues that we'll have to adapt to. We have older housing that's not all that well insulated. It's heated by oil, and this is a diesel car. So all of these will probably have to change in 30 years' time. Looking at the world population, the United Nations are very good on statistics, and the current rate of rise in the global population is about 200,000 per day. This means that we need to build a city about the size of Aberdeen every day, or a city the size of Glasgow every week. It's not sustainable. If we look at the way population is predicted to change, on this graphic, the pink and red areas are predicted to see a population decline over the next 30 years. The blue and purple areas are going to see a steep rise in population. And you notice Africa is all kind of blue and purple. This will have an effect on the average age. If we look at the distribution of pensioners, age 65 plus, as a percentage of the population now, we can see that areas in Europe are blue, which means a relatively high proportion of pensioners, but Africa has a relatively young population. Going 30 years ahead, you notice that lots of other areas go blue, even China goes blue, but Africa remains with not many older people. This implies that they're going to have poor life expectancy and remain in poverty, which is very sad. If we're going to have to look after older people better, then I think one area that will develop is what we would call microbiomedical systems. These are devices that can be implanted in the human body. We're all familiar with the cardiac pacemaker, which has been around for a long time and is not particularly small. We could implant in humans identity chips, rather like what we put in cats and dogs now. They could be adapted for other things. Here are two devices from the University of Edinburgh. One is a drug delivery chip that could be implanted into the human body. Think of it as a miniature blister pack, where each of the doses could be activated externally to release a measured quantity of drug right into where it's required. Here's another one, so-called lab on a chip. Here we have a silicon chip with 10 areas on the surface. Each area could be treated with a particular chemical, and under computer control, we can move a droplet of liquid, which could be a urine sample or a blood sample, from one patch to the next and observe it with a camera and thereby do chemical analysis on a chip. There's another device for drug delivery, but this one has incorporated into it a sensor which measures the problem in the human body, whether it's high blood pressure or low blood pressure or whatever it is. It measures that and administers an appropriate quantity of drug where it's required, when it's required. Now, if we get really smart, we know that some of the diseases and problems we have are related to our genetic makeup. There's some very good work being done by Professor Jim Wilson at Edinburgh, another Orcadian, and his team on relating genetic makeup to disease and medical history. We're all made of cells, and as you know, in the nucleus of the cell we have chromosomes, and in that we have DNA, deoxyribonucleic acid. This is the genetic code which makes us what we are. Now, in the 1980s, biochemical methods were developed to read the code, to decode our DNA. And it turns out that the DNA molecule is rather like a twisted ladder. And the rungs of the ladder are made up by pairs of what are called bases, and they always pair up in a particular way. And if you can unravel this and treat it chemically, you can extract from this and read the sequence of these bases G, C, A, and T. And that was done initially manually and then later with automated machines. Round about 2001, there was an enormous international effort to decode the entire human genome. This was an enormous task. It cost billions of dollars. And the early methods of doing it were still very expensive. It would cost about $100 million to decode someone's DNA. But in the intervening 20 years, a lot of technology has been developed to automate this process. So it's now down at about $1,000 per genome. The way to do this is to unravel the DNA, actually unzip it, so that you can see the individual bases on the single strand, which is called ribonucleic acid. Now, it would be really good if we could look at this electrically and interface it directly to a computer. And this is one method that has been tried and it works. Imagine we take the RNA and unzip it. Sorry, take the DNA, unzip it to create the RNA. And if we now have a tank with some saline solution, and the tank is divided into two by a membrane here, and in the membrane, there's a tiny little hole, size of a nanometer. We would say in Orkney it's awful peedy. It's really peedy hole. Now, if we apply a voltage across this tank, we will see a small current because the sodium ions and the chlorine ions will flow through this nanopore, this tiny hole. If we now introduce RNA into that, then that too will move under the influence of this voltage gradient. And as each base goes through the nanopore, it will change this current that we're measuring. And what we hope is that we'll be able to read out the sequence electrically. It sounds far-fetched, but it has been made to work. A company called Oxford Nanopore Technologies, spun out of the University of Oxford, have produced a device which will do this directly interfaced to a computer. And we heard on the news in August that this device is being used now to check for COVID-19. It's a big task to read the whole genome, but we don't always have to do that. We can sometimes get away with reading less than the whole one, but the whole length is 3.2 billion bases long. That's 3.2 times 10 to the 9. Now, supposing each pore can read 100 bases a second, that works out at 360,000 bases per hour. But because of read errors, the signal's not always perfect. We'd probably have to repeat it 100 times. So we need something much faster than that. So we need something like 1 million pores to read 3.6 times 10 to the 11 bases per hour. And it'd be ideal if we could get this down to like 10 minutes. And for that, we're going to need something like 10 million pores. Is that possible? Yes, because the number of pixels in your digital camera is probably about 20 million. So it's quite easy to get millions of pores on a chip. And that is what Oxford Nanopore Technologies have done. So let's finish off by looking at what might be in your new smartphone in 30 years' time. I've mentioned cameras already. Thermal imaging is a possibility. You can now buy a thermal imaging attachment for your mobile phone. You could have ears like a bat. You could do echolocation, range finding. You could have a lab on a chip for water and air quality monitoring. You could have a nose like a dog for sniffing chemicals and so on. I already mentioned health monitors and implanted devices. The obvious way is to interface those with your mobile phone, which is in your pocket. And through that, the mobile phone can transfer that information to your medical consultant via the internet. It could monitor your basic functions like heart and lungs, and if there's a problem, put in an automatic call for help. I'm sure you could think of other developments. So I would like to thank you for supporting the Orkney Science Festival. I hope that over the 30 years, the Science Festival has inspired a lot of young people to take up careers in science and technology. The country certainly needs more of you. So thank you once again for listening, and I'll hand over now to Howie.
Tom, that was fascinating. And while you've been speaking, a whole range of questions have been coming in. The first one is, in fact, going back in time a bit to the establishment of these various centres in Scotland and the UK, like the Microelectronics Centre. And the question is, are there any other centres like that in the UK at the moment? And are there comparable centres overseas?
Oh, yes. Going back a long time, the University of Sheffield was set up at the same time as the Edinburgh Microfabrication Facility, as it was previously called the EMF. And they specialized in gallium arsenide devices, what are called 3,5 compounds. And also the University of Southampton have very extensive microelectronics facilities. Initially, they were set up again around about 1980 to do bipolar devices, whereas Edinburgh was doing field effect transistors. So University of Southampton are still there. They still have a very active research group. So is the University of Sheffield. In Ireland, there is the University of Cork. And I suppose in Europe, there are several. One of the best is EMEC at the Catholic University of Leuven in Belgium. They really operate on a global scale. There are, in other countries, the United States, of course, and indeed in Japan, there are similar research organizations equipped to do what I would call microfabrication. That is to fabricate devices on silicon or other substrates.
And is there a kind of collaborative relationship between them, or a degree of rivalry?
Both, really. Obviously, funding for research is competitive. But in fact, there are usually very good personal links between people at these centres, because they meet at conferences and they tend to share ideas by email. I guess nowadays they're doing a lot of Zoom meetings rather than physical conferences. But yes, when I was working, I had quite a good relationship with the guy who ran the facilities at EMEC, for example, and also at some of the American research centers.
And there's a more technical question coming in. You mentioned aluminium early on for the tracks in those chips, and yes, there was a question about why aluminium as distinct from, say, copper.
Well, aluminium was the first. The reason it was used was that it was easy to etch. Copper is an absolute sod when it comes to etching. It's much more difficult to pattern copper at very small scale. But in fact, it has moved on, and at first they started adding copper to the aluminium to get better conductivity. And then eventually, when process techniques developed better, they went to copper interconnect because of its better electrical conductivity. Because one of the issues, if you try to make the track too small in cross-section, is that the current density becomes very high. You think of currents in the order of microamps as being very small, But if the track is very narrow and very thin in cross-section, you can end up with hundreds of amps per square meter in terms of current density. And if you go too high in current density, you get a phenomenon, particularly in aluminium, called electromigration, where the flux of electrons is sufficient to drag along atoms with it, and the metal actually migrates and becomes thin and then breaks just like a fuse blowing, which is terribly disappointing, of course. So we've moved from the cheap and cheerful aluminium to basically copper interconnect.
Now there's another question about materials, and this time it's about silicon, and greatly used, of course, in the industry. And there seems to be a lot of it out there in the world with all the sand, but you spoke, I think, of possible shortages or difficulties.
Oh, we're never going to run out of silicon. It's one of the most common elements on Earth. Really, you can extract silicon from rocks and sand almost anywhere. But the reason silicon has been so successful is that it's easy to create it in single crystal form, in a very pure form. It has its limitations in terms of its electrical properties, and there are materials that are better at high temperature and are better for faster switching and all that sort of thing. But for reasons of economics, primarily, the combination of economics and ease of processing, it has remained the dominant technology for the vast bulk of microelectronic devices. I hope that helps to make it clear, but don't worry, we're not going to run out of silicon.
Well, I had wondered when there was a mention of cost, but relieved to know that there's plenty of silicon out there.
Right.
Is extracting some of these materials, just extracting the pure form from the raw material in nature, can that be a problem sometimes?
Yes, in fact, extracting crystalline silicon from nature is very energy intensive. If you're worried about energy consumption, it is very energy intensive because it's done by producing a melt of silicon. Now, to melt silicon, you need a lot of heat. You need a very, very high temperature. And you then introduce a seed crystal into this crucible of molten silicon. And as you probably know from school days growing crystals, it grows very slowly, and you very carefully and slowly withdraw this crystal from the melt, and it grows, the crystal grows as you withdraw the crystal. And you end up with a thing like a large sausage of pure crystalline silicon, which you can then slice up into wafers and polish. And that's the raw material for making chips, making microelectronic circuits.
And are there new materials around the corner that might surprise us? Some very unusual exotic metal, for instance, or even some biological materials?
Yes, I just read the other day about some people who are planning to build a living computer that is going to use biological cells and their behavior in order to process signals. I really haven't a clue about that. I fear it could end up very smelly. I don't know. I've tended to keep away from biological devices like that, but that is an area that is being looked at. And also, the worry with Moore's law is that we're about to hit a brick wall, that we're going to run out of steam. And in fact, what has happened is, in order to maintain high computing speeds, people like Intel, instead of making the transistors smaller and smaller, which becomes much more difficult, much more expensive, they've tended to go for having lots of computers working in parallel. So you get computers that have 4 processors working in parallel, or 8 processors working in parallel. And that gives the same computing speed, but using 4 easier to make computers with slightly larger transistors in them. I hope that's clear. It's like having 4 people doing calculations in parallel. That's the equivalent of one person working 4 times as fast. That's the concept that they've gone for.
And there's a question about Moore's law and how far can it go, because it keeps on getting faster and faster, but there must come a point, presumably, when that's the maximum.
Yes, we're getting close to that. The thing is that I mentioned a figure of 10 nanometers for the smallest gate length field effect transistor. If you think that the atomic spacing in the silicon crystal is 0.4 of a nanometer, then that's only 25 atoms. Now, if you go to, say, half that dimension, say 5 nanometers, you'd be down to 10 or 12 atoms. And at that kind of number, quantum effects come in, and they might not all behave the way you expect them to. And it's felt that by the time you get to that kind of dimension, the behavior might become unpredictable and unstable. And so people are talking now about, well, why not use this as a feature and go to quantum computers which exploit quantum effects, and you might have more than two states. At the moment, we've state 0 and state 1. You might have something in between. Again, I have no experience of this. I may be talking complete nonsense, but I know it's on the horizon. We cannot go on shrinking forever. We're very close to the bottom limit.
There's also a question about new possible growth areas, in particular space. And the question is, what effects are the demands of the growing space industry having on microelectronics?
Well, it turns out that the beginnings of microelectronics really came from the space race. The Americans were behind the Russians, and the Russians had much bigger rockets than the Americans, so they could put heavier payloads into space. The Americans were really pushed to develop microelectronics to reduce the weight of the equipment that they were putting into space. And the early microelectronics developments were funded largely by the military and by the space demands. Now, in this country, in Scotland in particular, we have companies who are now building very small satellites, or CubeSats they're called. I think you've probably heard about this from the proposed space program in Scotland. And Scotland is very well placed to take advantage of this, because there's considerable expertise now in producing very small, very light satellites, all based on state-of-the-art microelectronics. A Scottish success story, really.
It's fascinating, Tom. There are so many more questions coming in, but time is moving on. And just before thanking you very warmly for getting us off to such a good start with the festival, I'd like to also thank the technical team and to mention to everybody watching and listening, our next item at 1 o'clock today will be Sheep on the Shore, about another area at the frontiers of research about seaweed diet and animals and the effects that have been found over the years with North Ronaldsay sheep. Well, that's at 1 o'clock. But in the meantime, to round off, thank you, Tom, very much indeed. It's been a fascinating insight, and goodbye for now.
Well, I would like to thank the technical team as well for helping to put all this together. Thank you very much.